Welcome! In the next few minutes, you will watch a brief, clear summary of heat transfer fundamentals, focused on conduction, forced convection, and natural, free convection. You will see the key ideas when each mode dominates and the practical intuition needed for engineering analysis and design. Let us begin.
The fundamentals of heat transfer. So we're looking at this amazing visual guide that really breaks down exactly how thermal energy moves. And this is super important for anyone studying physical systems or engineering, especially when you're dealing with heating and cooling, things like heat exchangers. Okay, so here's what you absolutely need to know. First, you've got the three basic ways heat gets around. There's conduction. That's heat transfer through direct contact, kind of like when a hot pan heats your hand. Then you have convection, which is heat being carried by a moving fluid. Think of the steam rising from boiling water. And finally, there's radiation. That's heat moving through electromagnetic waves, like the warmth you feel from the sun traveling through space. All right, second, the guide dives into the two main methods for actually designing these systems. And which one you use, it all comes down to the data you have. If you know all the inlet and outlet temperatures, you're going to use the LMTD method. The whole point there is to size a brand new heat exchanger. But if your outlet temperatures are a mystery, you switch to the effectiveness NTU method. That's all about predicting the performance of an existing one. So yeah, getting a handle on these modes and methods is just critical to manipulating energy in pretty much any system you can think of, mechanical or natural.
Visualizing heat transfer using the electrical resistance analogy. So why does this matter? Well, it basically lets us treat complex heat flow just like a simple electrical circuit. And that's absolutely crucial for understanding how things like insulation and materials really work in construction and engineering. First up, the core concept. It really just boils down to this. Heat flow acts exactly like an electrical current, kind of like Ohm's law. So you have heat flow, that's your current, the temperature difference across a system, that's the voltage pushing it, and thermal resistance is, well, it's the thing trying to stop it. Second, let's talk about where this resistance comes from. You've got two main types. There's conduction resistance, which is just heat moving right through solid stuff, like a wall. Then there's convection resistance. This happens when heat tries to move through a fluid, like air or water, and its resistance depends a lot on how fast that fluid is moving. And finally, this is where the analogy gets super useful, when we deal with common geometries. Picture a wall made of multiple layers, say brick, insulation, and then drywall. Each of those layers just acts as a resistor in series. So to get the total resistance, you just add them up. The resistance of the brick plus the insulation plus the drywall. Simple. Understanding thermal resistance is really the key to controlling heat transfer, whether you're engineering a pipeline or just insulating your home.
Critical insulation thickness. Okay, so let's talk about something that sounds a bit backward. The insulation paradox. It's this really counterintuitive idea that when you add insulation to something like a small pipe, you can actually make it lose more heat, not less. Here's what you need to know. First up, you have to understand something called the critical radius. Just think of it as the insulation's tipping point. It's the specific outer radius where heat loss from the pipe hits its absolute maximum. To find it, you simply take the insulation's thermal conductivity, which we call K, and divide it by the convection coefficient, or H, basically how fast heat escapes into the surrounding air. Second, what's actually happening here? Well, it's a balancing act between two forces, conduction and convection. Insulation is great at slowing down heat transfer through the material, that's the conduction barrier. But here's the catch. Adding insulation also increases the total surface area, which gives heat a bigger window to escape into the air through convection. And finally, this is where it gets really interesting for small pipes. If your pipe's radius is less than that critical radius, adding insulation will actually increase your heat loss. I mean, you could see heat loss jump from about 85 watts per meter all the way up to over 105. It's only when you insulate past that critical radius that the insulation finally starts doing its job, and heat loss begins to drop. So remember, effective insulation isn't just about adding more thickness, it's about calculating that critical radius to make sure you're actually saving energy, not wasting.
Heat transfer and fins. So, fins. You see them everywhere. They're these super important engineering parts designed to make things cool down faster. We're going to break down the physics, the key calculations, and pretty much everything you need to know about how they work. Okay, first up, the physics. It all boils down to this thing called the energy balance principle. Just picture this. Heat is trying to travel along the fin, that's conduction, but at the very same time, it's escaping from the surface into the air around it. That's convection. This constant balancing act, energy in versus energy out, is what we need to solve for. Second, let's talk about the math. Modeling what happens right at the very tip of the fin can get, well, tricky. So to make life easier, engineers use three main assumptions. There's the infinitely long fin model, which just assumes the tip is so far away, it's the same temperature as the air. Then you've got the insulated tip, where we pretend no heat escapes from the end at all. And then there's the most realistic one, the convective tip, which actually accounts for heat leaving from that tip surface. And finally, how do we know if a fin is any good? Well, that's where fin efficiency comes in. It's basically its report card. It compares how much heat the fin actually transfers to the absolute most it could possibly transfer. That perfect scenario? That's if the entire fin somehow stayed as hot as its base. So, efficiency tells you how close to perfect you're getting. Grasping that energy balance, the different tip scenarios, and what efficiency really means gives you a fantastic foundation for analyzing pretty much any fin design out there.
Heat transfer fins. Fins are that crucial engineering trick, like the vanes on your computer's CPU cooler, that are all about getting heat away from a surface and into the air. But how well they work isn't always so simple. First, it's all about maximizing surface area. This gives heat more space to escape through convection. Now, to measure this, we use something called fin efficiency. Think of it like this. It's the ratio of how much heat the fin actually transfers compared to the perfect ideal amount it could transfer if the entire fin stayed as hot as its base. Second, the material is just absolutely critical. I mean, if heat can't travel down the fin easily, then all that extra surface area doesn't do you any good. And this is where the numbers get really interesting. Highly conductive copper, it's got an efficiency of about 95.5%. But a poor conductor like glass, wow, it just plummets down to only 12.4%. And finally, we've got to talk about the real-world problems. Believe it or not, fins can sometimes hurt heat transfer, especially in high convection situations like boiling. But the biggest roadblock is something called thermal contact resistance. It's basically a tiny, insulating layer of air trapped in microscopic gaps right where the fin joins the base, and it causes a huge temperature drop. Its effect really depends on surface roughness, the pressure holding it all together, and the gas in those voids. So optimizing heat transfer with fins really means understanding that efficiency is just as much about the material you choose as it is about minimizing that pesky contact resistance.
The visual guide to convection and the transition from laminar to turbulent flow. We're diving into a really fundamental question in fluid dynamics. How do we know when a fluid's flow is going to go from smooth and predictable to, well, a complete chaotic mess? So let's break down the three key takeaways you need to understand this critical shift. Okay, first up, you've got to know the two basic types of flow. On one hand, you have laminar flow. Think of it as smooth and orderly, the fluids moving in these neat, parallel layers. But then you have turbulent flow, and that's the complete opposite. It's chaotic and messy, with all these random swirls and churns. This is great for mixing things up, but it also creates a ton of friction and wastes energy. Second, how do we predict when that shift will happen? Well, that brings us to the Reynolds number, or RE. It's basically a value that compares the fluid's momentum, how fast it's trying to go, to its viscosity, or how sticky it is. When momentum really starts to overpower that stickiness, the Reynolds number gets high enough, and that's when things flip from stable to chaotic. And finally, that critical Reynolds number isn't a one-size-fits-all thing. It totally depends on the geometry. For flow inside a pipe, things can go turbulent when the Reynolds number gets above just 2,300. But for that same fluid flowing over a flat plate, you'd need a Reynolds number way higher, over 500,000, to see that same kind of turbulence. So, by defining the Reynolds number and these critical thresholds, you've got the essential framework for understanding and predicting how fluids behave in pretty much any system. Calculating heat transfer in pipe flow. So this is your quick breakdown of the key empirical correlations engineers use to figure out thermal performance inside pipes. And you gotta know, all of these calculations really depend on the flow's Reynolds number, or RE. First up, The flow regime is everything. You absolutely have to know if your flow is turbulent or laminar. Turbulent flow, that's when your Reynolds number is over 4,000, and laminar is when it's below 2,300. For your standard, smooth, turbulent tubes, the classic Dittus-Boelter equation, that's your go-to starting point. Second, you got to account for changes in viscosity. So what if you have a huge temperature difference? I'm talking big gradients that really mess with the fluid's viscosity, especially right near the pipe wall. Well, for that, you're going to want the Cedar-Tate relation. It cleverly uses a ratio comparing the bulk fluid viscosity to the viscosity right at the wall, which keeps your calculations accurate for both flow regimes. Finally, what about non-circular pipes or really long ones? Okay, for non-circular ducts, you have to calculate the hydraulic diameter first. That's just 4 times the cross-sectional area divided by the wetted perimeter. And for fully developed laminar flow in super long tubes, the Nusselt number actually approaches a constant value of 3.66, assuming the wall temperature is constant. Applying the correct empirical correlation based on your flow regime and pipe type is the absolute key to accurate thermal system design. How fluid flow over a cylinder drives heat transfer. So if you're an engineer, someone designing thermal systems, think piping or engine parts, well, getting a handle on how forced convection works across something like a cylinder is, it's absolutely crucial. So let's just cut to the chase. Here are the 3 big takeaways you really need to know. Okay, first up, the basic physics. It really all starts with pressure gradients causing the flow to separate. See, as a fluid moves past the cylinder, it actually slows down on the backside. And when that happens, the pressure shoots up, and that's what causes the flow to reverse, creating that turbulent wake you see behind it. Second, this whole process, it's pretty much all governed by the Reynolds number, RE. This number tells you what kind of flow you're dealing with, and believe me, that massively affects your heat transfer. For example, once that RE number gets high enough, the flow goes from being all smooth and predictable to oscillating, and that's when you get that classic Kármán vortex street. It just completely changes the thermal game. And finally, what's the big implication here? Well, all that chaotic, swirling motion in the wake, it actually ramps up the local heat transfer rate a lot. And since the physics get super complex, this is where we as engineers bring in a bit of a shortcut. We use a proven formula, one that links the Nusselt, Reynolds, and Prandtl numbers to get a really solid calculation for the average heat transfer without getting bogged down in all the crazy math. So really, understanding that connection between pressure, the Reynolds number, and that flow separation, that is the key. It's essential if you want to design effective forced convection systems and really nail your thermal management. Calculating heat transfer across tube banks. So if you're an engineer and you need to get a handle on the heat transfer coefficient for fluids flowing over tube banks, well, this is for you. We're going to break down the essential process step by step. Okay, first up, it all starts with 2 things, the geometry and the velocity. You've got to know if your tube bank is in line, a simple grid, or if it's staggered with that offset pattern. Then, and this is crucial, you have to calculate the maximum velocity. That's how fast the fluid is moving as it squeezes through the tightest spot between the tubes. Honestly, everything else pretty much hinges on this one number. Second, you take that maximum velocity and use it to find your maximum Reynolds number. This number tells you the exact flow regime you're working with, and that dictates which empirical correlation you should grab. For example, you might use Grimeson's if you have 10 or more rows deep, or maybe Zakalska's for 20 or more. These correlations help you solve for the Nusselt number, which is what ultimately gets you to that heat transfer coefficient you're looking for. And finally, you always have to adjust for the real world and account for uncertainty. So, let's say your bank has fewer rows than the correlation assumes. You've got to apply a correction factor. But here's the big one, really. This isn't perfect math. These are relationships based on lab data, which means there's a built-in uncertainty of about plus or minus 25%. You have to plan for that. So, getting the geometry and velocity right is absolutely key. But always remember to factor in that hefty 25% uncertainty when making your final calculation.
Forced convection empirical formulas. Think of these formulas as your go-to guide for figuring out convective heat transfer. They give you a quick, accurate answer whether you're dealing with fluid flowing inside a tube or across an object. Super useful for engineering. Okay, so first up, everything is built on 4 key numbers. You've got the Nusselt number. That's all about how effective the heat transfer is. Then, and this one's a big deal, the Reynolds number. It tells you if the flow is smooth, laminar, or chaotic and turbulent. Next is the Prandtl number, which is about the fluid's own thermal properties. And finally, because not all pipes are round, right, we use the hydraulic diameter to make the formulas work for non-circular ducts too. Second, when you're looking at flow inside a tube, it really all depends on that Reynolds number. If the flow is turbulent, you'll probably use the Dittus-Boelter equation. It's a real workhorse. But, and this is key, it only works under very specific conditions. Now, if your flow is laminar, you have to toss that out and use a totally different formula, one that depends on the tube's length and has its own strict set of rules. And finally, for external flow, so fluid moving across an object, the shape is everything. For something like a cylinder, there's a general formula, but the constants in it change a lot depending on the Reynolds number. But for a sphere? Nope. You need a completely different specialized formula just for that shape, with its own set of constraints to make sure you get the right answer. So, when it comes down to it, if you understand these core numbers and know your context, internal or external flow, and what the restrictions are, you can grab the right empirical formula instantly and know it's the right one.
Natural convection. So let's talk about the gentle current. You know, it's how your room radiator or even huge atmospheric currents move heat around, all without a fan. How's that even possible? Okay, there are a few key things to get. First, the engine behind it all comes down to density and buoyancy. It's actually pretty simple. When you heat up a fluid, like air or water, it expands and gets less dense, lighter. And that lighter fluid naturally rises. That rising motion is what drives the whole circulation. Second, what about the physics that actually predict how this flow moves? Well, if you look at fluid moving along a surface, its speed isn't constant. It's zero right at the wall, hits a maximum a little ways out, then goes back to zero. This whole flow is governed by what's called the Grashof number. Basically, it's a crucial ratio that tells us if the flow is going to be smooth and predictable or if it's going to break down into chaotic turbulence. And finally, you got to know the difference between natural and forced convection. Natural convection is totally spontaneous. It just happens because of those density changes. Forced convection, on the other hand, needs an external push, like from a fan. That's exactly why your computer's CPU heatsink needs a fan, to get rid of heat way faster than a gentle, natural current ever could. So really, natural convection shows us how simple laws of density and buoyancy create these gentle but incredibly powerful currents that move heat everywhere.
Calculating free convection heat transfer. So, you're dealing with free convection, right? That heat transfer that happens just because of temperature differences making fluids move. Well, we're going to cut right to the chase and give you the essential formulas engineers use to get this done fast. First, it's all about one foundational formula. Your goal is to find the Nusselt number, or nu. And the equation is pretty simple. Nu equals C times the Rayleigh number, R, raised to the power of m. Honestly, the whole game is just finding the right constants, C and m, for your situation. Second, the secret to finding those constants is the Rayleigh number, or Ra. Think of it as the Grashof number, which is all about the buoyancy, multiplied by the Prandtl number, which handles the fluid's properties. Now, what's so critical about Ra? It tells you if your flow is laminar or turbulent, and the magic number is 10 to the 9th. Below that, you've got laminar flow. Above it, it's turbulent. Finally, let's get to those constants. The good news is the m value is super predictable. For a laminar flow, it's always 1/4, and for turbulent, it's 1/3. You just have to pick the right C for your geometry. For a vertical plate in laminar flow, C is 0.59. If it's turbulent, C drops to 0.10. For a horizontal cylinder, it's almost the same pattern. C is 0.53 for laminar and 0.13 for turbulent. So really, mastering that Rayleigh number and matching it to your object's geometry, that's the shortcut to nailing your free convection calculations every time.
All right, so these correlations are basically your go-to guides for modeling natural convection, heat transfer driven by density differences. And it all comes down to the object's shape. We're going to look at the formulas based on geometry and two critical inputs you've got to get right. It's all about the link between the Nusselt, Grashof, and Prandtl numbers, which tell you about the heat transfer, buoyancy, and fluid properties. First up, let's talk about horizontal cylinders. The formula for this shape is kind of the gold standard. It's super detailed and reliable across a massive range of values. We're talking from 10 to the -5 all the way up to 10 to the 12th, so it's definitely your main reference. Oh, and there's also a simpler version for laminar flow if you just need a quick estimate.
Second, when you're dealing with simpler shapes, like horizontal plates or even irregular solids, the formula gets a lot simpler. It's basically nu equals c times the product of GRO and PR, all raised to the power of m. But here's the catch. For horizontal plates, those constants, c and m, they actually change depending on the plate's orientation. So you got to know if your heated surface is facing up or down, because the physics are completely different. And finally, you absolutely have to nail two critical inputs. Your whole calculation depends on them. First is the film temperature, where you evaluate your fluid properties. And that's easy. It's just the average of the wall and the ambient temperatures. The other one is characteristic length, or L. For a horizontal plate, it's just the surface area divided by the perimeter. For irregular shapes, you just estimate it as the path the fluid takes along the boundary layer.
So, just remember, apply the right correlation for your object's shape, nail the film temperature and characteristic length, and you'll get a reliable estimate for natural convection heat transfer.
Thank you for watching Part 1 on conduction, forced convection, and natural or free convection. If you found this quick summary helpful, please continue to Part 2, where we will cover boiling, condensation, radiation, and heat exchanger design.